Okay, so in the last class, we were basically studying Huffman codes. We saw an implementation of Huffman codes in Python, right? But before that, we showed that Huffman codes are optimal prefix-free codes. Among all possible prefix-free codes, Huffman codes achieve the minimum expected length. All right, and these are also canonical prefix-free codes, which means that they satisfy those three properties. Towards the end of the last class, where we did this experiment with English text, we saw that Huffman codes, so we had this English text file that we wanted to compress. And the way we went about in designing a compressor for this English text file was that we first computed the empirical frequency of letters in this English text file. And we took that as the probability mass function, designed a Huffman code for that, for the empirical frequencies essentially. And then just implemented the Huffman code and encoded the text file character by character. And in doing so, we saw that the rate that we could achieve was somewhere around 4.16 bits. All right. And if you did a naive form of encoding, wherein you took the each character separately, represented them using the alphabet size. The alphabet size is 26, so each character can be represented using 5 bits. So you would need a rate of, so in the uncompressed form, the rate would be 5 bits. All right. So we got this particular rate by encoding the whole file character by character. But what we can also do is try to compute sort of the total entropy that is there in the file. All right. Which one? Correct. R uncoded. All right, or R uncompressed. The above is the compressed file. That's the compressed rate that we got by symbol-wise Huffman coding. Okay. And this was found to be close to the entropy. I'm sorry, I think it was not 4.16 bits, but rather something closer to 4.19 bits, right? 4.19 bits. And the entropy obtained from the empirical frequency was found to be around 4.16 bits. Okay, so if the entropy is 4.16 bits, we're getting close to that. So that's a good sign. But now all of this, the design of our scheme was kind of implicitly assumed that the symbols are memoryless. Right, so we have a memoryless source that we wanted to compress using symbol-wise encoding. What we could instead do is the following: we take pairs of symbols, all right, and try to encode them. So I have a text file, maybe which has 10,000 symbols. I divide them into blocks of 2 symbols each. So the total number of sort of blocks would be 5,000. So I have a 10,000 character long text file. Pairs of characters form a symbol. So now I have a total of 5,000 symbols. If I try to design a Huffman code for this block, right, then what I would get would be close to the entropy of x1, x2, the joint entropy of x1, x2 by 2, which can be obtained by computing the empirical frequencies of pairs of symbols. Right, so the empirical frequency of a pair of symbols, let's say x1 and x2, is essentially the number of, let's suppose I have an n length source file then this would be the empirical frequency of any pair of symbols. So you look at consecutive symbols, certain symbols occur in pairs, and this is the frequency of those pairs. This you can treat, if the source is assumed to be stationary, then this quantity is going to be roughly equal to pxi xi plus 1, the probability mass function of any consecutive pair of symbols. Okay, this is assuming that it's a stationary source. So if I try to do that, let's say I compute this particular quantity for all possible pairs of characters and find this joint entropy, this quantity would turns out to be approximately equal to 3.89 bits. If the source were truly memoryless, then h of x1, x2 by 2 would just be h of x1 plus h of x2 divided by 2, which would still be 4.16 bits. But the fact that h of x1, x2 by 2 is something which is less than 4.16 bits means that there's some amount of memory. So each character depends on the previous character. I can extend this idea. I can look at triples of characters. And that turns out to be roughly 3.64 bits. And if I, similarly, I can go on like this. This turns out to be roughly 3.32 bits and so on. So if I group together multiple symbols, take blocks of symbols at a time and try to compress that, I can potentially achieve a much smaller rate. All right? But all of this comes at a price, and that price is computational complexity. If I look at pairs of symbols, then my alphabet size, assuming that we have in the English alphabet, only lowercase characters, mind you. If we have only the lowercase characters and I want to encode pairs of symbols, then I have to design a Huffman code over an alphabet size of 26 square. In general, if I want to group together k symbols, the alphabet size becomes 26 to the power k, which grows exponentially. Right? And the complexity of even of encoding, decoding, even designing the Huffman code will now grow exponentially with k. So grouping together symbols has the benefit of reducing the compression rate, but it also increases the computational complexity. And this can blow up very fast. So even if you take, let's say, k to be equal to, say, 7, x to the k turns out to be larger than, I think, 8 trillion. That's a lot. Even storing the probability mass function can potentially take several gigabytes of space. All right.
So given that you can do as much computation for it, what is the value of the h of x power n by n converging to?
Okay, you mean what will it converge to? I won't answer it right now, right? But for any stationary source sequence, right? If the source were first order Markov, okay, so if, so what does h of x to the k by k converge to, right? That's the question. So if this is a, say, mth order Markov chain, we're assuming that throughout we're assuming that all of this is stationary. That is, the distribution of any chunk of k symbols is the same no matter where you see in the source sequence. All right. Then what does we've seen this? What does this converge to?
Transition probability.
Correct. Not the transition probability, but the conditional entropy of h of x m plus 1 given x1 through xn. All right. And we know that conditioning can only reduce entropy, right? So for example, h of xm plus 1 given xm is going to be larger than h of xm plus 1 given xm minus 1, and so on. So if the true source distribution is an mth order Markov chain, then the rate will keep decreasing as I increase k up to a certain point, right? Until I hit m. Once I hit beyond m, I don't get any significant benefits, right? But until m, I can get a significant benefit, potentially get significant benefits. Right. Any other questions?
What if it is an infinite Markov?
Which one?
The Markov identity.
So you mean to say that m is very, very large, right? That can happen. For example, if there is a very long range dependence, but at least for practical situations that we see, for example, English text, the order is not, it can be a bit large, but not too large. All right. But later on, maybe after a couple of classes, we'll see an approach that will work irrespective of what the order of the Markov chain is. Now, all of what I'm saying, you can achieve, let's say, this particular rate only if the size, the length of your source is significantly larger than m. Right? Otherwise, it doesn't even make sense because you don't even see so many symbols. So there's no way you can achieve this particular rate. So if you were to achieve the entropy rate of an mth order Markov chain, then you would have to have a source sequence n which is significantly larger than m. And that is, we will always operate under that particular assumption. All right. But as it turns out, any stationary and ergodic source can be well approximated by an mth order Markov chain for large enough m. The degree of approximation would depend on m, but taking an m that is sufficiently large is usually good enough. But the point here is that even if we do, let's say, symbol-wise encoding, that is, we treat it as an ID source, but the true distribution is some Markov chain, we can still achieve h of x. And we can get pretty close to h of x. All right. So we see two problems with the approach that we followed using Huffman codes. The first problem is that the entropy rate could be significantly smaller than h of x, the first order entropy. All right. So that's one problem. We are not making use of dependence in the source. The second problem is, even if the source is IID, all right, the rate that we achieve is going to be something less than h of x plus 1 bits for if we use symbol-wise Huffman coding. And so the expected length for a source sequence of length n can only be guaranteed to be n times h of x plus n bits. If the source has small entropy, let's say 1 or 2 bits, even if the alphabet size is large, the source has entropy close to 1, then the expected length can be fairly large. For example, this particular term can dominate over n h of x, n times h of x. So that's another problem. And this can also potentially be solved even for a memoryless source. We can solve this by grouping together symbols, taking blocks of k symbols each. So if we take suppose we code blocks of k symbols, we can achieve a rate equal to k times or h of xk plus 1 bit divided by k, right? Because the overall rate is going to be n by k. I have n by k blocks, and each block is encoded using h of xk, at most h of xk plus 1 bits, divided by n, which is h of xk by k plus 1 by k. For a memoryless source, h of xk is just k times h of x, which is simply h of x plus 1 by k. So by coding blocks of symbols, I can also reduce this penalty that I had to pay because I was forced to design a prefix-free code. But now I'm not designing prefix-free codes for symbols, but rather blocks of symbols, which means I also have to decode blocks of symbols and encode blocks of symbols. And the price I have to pay is that the computational complexity now will grow exponentially with k. All right, any questions? Okay. So what we want to now do is design a code or try some other approach wherein I don't have to pay this extra penalty. Somehow I want to be able to encode groups of symbols or blocks of symbols. This may not be the best code for blocks of symbols, but I can encode and decode very efficiently. All right? I don't want to pay this exponential complexity penalty. All right. So towards that, we'll look at a different code. So far whenever we've been talking about prefix-free codes and Huffman codes and even the Shannon code, we were always interpreting codes and visualizing codes in terms of the code tree. All right. Now we'll take a different approach. All right, and we'll instead visualize them through their probabilities. So let's say that we are given some PMF Px on an alphabet. We'll assume that this alphabet is 0, 1, 2, 3 up to m minus 1. If the true alphabet is not 0, 1, 2, 3 up to m minus 1, then I'll map the symbols to 0, 1, 2, 3 up to m minus 1. Okay. There's a specific reason why I'm choosing this particular alphabet, and we'll see later on. There are m symbols, and the symbols are going to be labeled 0, 1, 2, 3 up to m minus 1. So for this, I'll define the CDF f of x, which is summation overall x prime less than or equal to x. The symbols in the alphabet are now ordered, right? It's 0, 1, 2, 3 up to m minus 1. So this definition makes sense. So this is the standard CDF, nothing fancy over here. But I'll also define the modified CDF. Which I'll call f bar of x, which is equal to summation x prime less than x px of x prime plus px of x divided by 2. Right, this is some quantity. I've just defined this, but this is based on the probability mass function Px. From this, all right, so there's nothing sophisticated about this, just a simple definition. Now for this, let's suppose that this is some number, this quantity f bar of x is going to be some number between 0 but strictly less than 1. We're assuming that all symbols have strictly positive probability. All right, if not, we can just remove that from the alphabet. So this f bar of x is a number between 0 and 1, strictly less than 1. What I can do is look at the binary representation of this particular number. All right. So this, for example, it's some 0.2619 something. This would be the decimal representation of this particular number. I can also represent this in binary as, I don't know, 0.101 01110 something. All right. So corresponding to each f bar x, I have some binary sequence. All right. Our approach will be to design a code purely based on this binary representation of fx. So let's say that I truncate f bar of x to L of x bits. When I say truncate f bar of x to L of x bits, what I mean is I only take the first L of x number of bits and then remove the rest of the bits following that. suppose I do this, I'm guaranteed, so let's call this f bar of x L of x. So this is the truncation of f bar of x to L of x bits. Then what I'm guaranteed is that f bar of x truncated to L of x bits, this quantity is less than or equal to f bar of x, because I've thrown away some of the bits after a certain point, but this is going to be greater than or equal to f bar of x minus 1 by 2 to the power L of x. Do you agree with this? Right? I mean, why is this true? Well, what does it mean to truncate f bar of x? So let's say that f bar of x has the following binary representation. Let's say it's 0.b1, b2, b3, and so on. For example, this could be 0.011011111. All right. So this is effectively the same as saying summation I equal to 1 to infinity bi 2 to the power minus I. So if the binary representation of this particular number is 0.b1, b2, b3, and so on, then the number f bar of x is going to be exactly equal to summation I equal to 1 to infinity bi 2 to the power minus I. Do you, at least you agree with this, right?
So multiply with locally L of x, and then that would just be the property flows on.
True. There's a reason why I want to also bring this up. Okay, we want to look at this from various angles, but you're right. All right. So f bar of x truncated to L of x bits is simply summation I equal to 1 up to L of x bi 2 to the power minus I. So f bar of x minus the truncation is summation I equal to L of x plus 1 up to infinity bi 2 to the power minus I, which is greater than or each bi can either be 0 or 1, so this quantity is less than or equal to summation I equal to L of x plus 1 up to infinity 2 to the power minus I, which is just 2 to the power minus L of x. All right. Questions? Okay, great. So, I mean, let's perhaps take an example. So let's say that I take the distribution to be something. Let's say it is 0.42. So this is the PMF. Okay. Let's look at the binary. Let's try to write a function to compute the binary representation of any number. So I have a number A which is guaranteed to be between 0 and 1. I want to compute the binary representation of this number. How should I go about this? Correct. So let's say that the resulting binary representation is a string. Stop it. Let's see. To L bits. Let's say I just want to compute the first L bits of the binary representation. What should I do? I should first multiply the number by 2. If this is greater than or equal to 1, then the next bit in the binary representation should be 1, otherwise it should be 0. Equal to 1. Then S plus 1. Else S plus 0. Let's test this. Say point 7, 5. I want to find the first 4 bits in the binary representation. It's 1100. Let's do another sanity check. Something wrong. Yeah. So it's fine. Okay, so now let's try to find the binary representation of all of these probabilities over here to, let's say, the first 7 bits each. So the first 5 bits in the binary representation. X in 6. All right, so this would essentially be the binary representation. Right. Fine. So you can see that at least let me do something more. Let me take 8 bits in the binary representation. All right, so this gives some sequence, right? For each symbol in the alphabet, I'm computing a binary sequence using this particular approach. Now let's say I truncate each symbol to the following number of bits. X is the seal of log 1 over P of X, right? So this is what we used for the Shannon code. This is the length of the code word sequence. For each symbol was chosen to be seal of log 1 over P of X. But I'll go a step further. I'll add another bit. Okay, so these code word lengths are going to be 1 bit longer than what the Shannon code would assign them. And let us say that, so these are the lengths. If these were the code word lengths for the distribution, then the expected length would be into Lx So this would be 3.84 bits roughly, whereas the entropy would be P times this would be 2.28 bits. So it's much larger than the entropy, but fine. Let's just bear with me for now. So let's say that I do the following. The code words are going to be the binary representation of not P of x exactly. I'll have to first compute this f bar of x, which is x minus 1 plus P of x right, so this is what f bar would look like. Question? Okay. So this is what f bar would look like. So it's 0.2, 0.5 something, 0.68, 0.79, 0.89, and 0.966. Okay. Let's say that I take f bar and truncate f bar to L of x bits, which is C log 1 over P of x plus 1 bits. So the code words are equal to, what is the name of the function? Compute binary of f bar of x to L of x is happening. Right, so these turn out to be the code words. And if you notice carefully, this forms a prefix-free code. Right. So just to recap, what I did was I took the PMF, I computed the modified CDF, and then I truncated the modified CDF to L of x bits, which is ceil of log 1 over p of x bits, and then just took that binary sequence and used that as the code word. The L of x number of L of x bits following the point as my code word. And surprisingly, that happened to be a prefix-free code. Let's just test this on a different distribution. Let's just take some distribution of, say, length 5. All right, this is some distribution. Looks like a very ugly distribution. Let me change that. Okay, this is some random PMF. Again, let me compute f bar. Have 5 symbols. This is f bar, and I compute the code words. I have to compute L of x. And then compute the code words using the same approach. I'm sorry? What was P again? Yes? Ah, sorry. I didn't realize that. Correct. So now, okay. All right. So this is another code for a different distribution. But again, if you notice carefully, this is also a prefix-free code. So no matter which distribution I take, if I use this particular approach, I'll end up with a prefix-free code. All right. So let's see why that is the case. it seems a bit magical at this point, but why is it actually going to be a prefix-free code? So first, remember, we're taking f bar of x and truncating this. So f bar of x is something, say 0.b1, b2, and so on. Let's take another x prime, which is not equal to x. So f bar of x prime is, say, 0.b1 prime, b2 prime, b3 prime, and so on. So what is a bad situation that we want to avoid? We don't want, so we truncate f bar of x to a certain number of bits and f bar of x prime to some other number of bits. And we want to ensure that none of these two truncations are prefixes of the other. Correct? So when can that happen? So when is f bar of x truncated to L of x a prefix of f bar of x prime truncated to L of x prime? So let's say that this quantity is 0.b1, b2, b3 up to bk, and this quantity is 0.b1 prime, b2 prime up to b, let's not call this k, but b l prime. So for this to be a prefix of this, firstly, k should be smaller than or equal to L, and the first k bits of this should be equal to the first k bits of the second one. So b1 equal to b1 prime, b2 equal to b2 prime, and so on. Bk should be equal to bk prime by definition, nothing fancy here. But then what can you say about f bar of x truncated to L of x minus f bar of x truncated to, or I should say f bar of x prime truncated to L of x prime bits minus f bar of x truncated to L of x bits. So if this is a prefix of this quantity, then which of these two numbers would be larger? The second one would have to be larger. Okay, but you agree with that. So this quantity should obviously be greater than or equal to 0. But what can I say? Can I give an upper bound on this particular quantity? Correct. So this should be less than or equal to 2 to the power minus L of x. Do you all agree with this point? Okay. So the code word for x can be a prefix for the code word for x prime only if this difference is less than or equal to 2 to the power minus L of x. So if you want to show that this is a prefix-free code, we must show that this cannot happen. All right, so we want to show that these are separately spaced apart. All right, they're sufficiently spaced apart. So let's take some f bar of x prime and f bar of x. Let's take two neighboring x and x prime. All right, if x prime is greater than x, then f bar of x prime is going to be greater than f bar of x, just by our construction, because it's the modified CDF. All right, so let's take x prime to be equal to x plus 1. All right, and let us look at this difference. F bar of x prime truncated to L of x prime minus f bar of x truncated to L of x. So this is less than or equal to f bar of x prime truncated to L of x prime minus f bar of x. Sorry, let me, this is greater than or equal to this quantity minus f bar of x, because f bar of x is the untruncated version, so that quantity can only be larger. So let's so this quantity can only be smaller. So this quantity can only be larger. So this quantity is going to be smaller than this particular quantity. All right. Great. So now what is f bar of x prime equal to in terms of f bar of x? I claim that this is equal to f bar of x prime is going to be equal to f bar of x plus p of x plus p of x prime. Because if you recall, f bar of x is summation over a less than x p of a plus p of x divided by 2. So f bar of x plus 1 is going to be equal to summation a less than x p of a plus p of x plus p of x plus 1 divided by 2. I'm sorry?
Ah.
That's right. So this should be this by 2 plus this by 2. Right. Any questions? Okay, so this is, since I'm truncating this to L of x bits, this quantity is greater than or equal to f bar of x plus p of x by 2 plus p of x prime by 2 minus 1 over 2 to the L of x minus f bar of x. Just from that earlier calculation that we did. These two cancel, so this is p of x by 2 plus p of x prime by 2 minus 1 over 2 to the L of x, which is 1 over 2 to the seal log 1 over p of x plus 1 . So this quantity is greater than or equal to p of x by 2, right? Because seal of log 1 over p of x is less than or equal to log 1 over p of x. So the denominator, so the whole thing is greater than or equal to 1 over 2 to the log p of x plus 1. Which is just p of x by 2. Sorry, this is less. The quantity is less than or equal to this, so negative of that is greater than or equal to this particular quantity. So this is greater than or equal to p of x by 2 plus p of x prime by 2 minus p of x by 2, which is p of x prime by 2, which is strictly greater than 0. I'm sorry, should have done it a bit. Greater than. Sorry, what did I want to show? Bar of x. Okay. what I wanted to show there was a lower bound, right? So let's take f bar of x prime minus f bar of x sorry, I think I got the inequalities mixed up, right? So this quantity, let's do it more carefully. Right. Let's just disregard what I did previously. Let's take f bar of x L of x. This is less than or equal to f bar of x. So this quantity is I want to prove an upper bound. So this quantity is less than or equal to f bar of x prime minus floor of or truncation of f bar of x to L of x bits. I'm sorry, I'm sort of mixing this up. Show is sorry, the previous thing was correct. So let's see. So this quantity is greater than or equal to f bar of x prime truncated to L of x prime bits minus f bar of x truncated to L of x. So this is greater than or equal to f bar of x. All right, just from the fact that this quantity is less than or equal to this particular quantity, so the negative is greater than or equal to this. Now this is equal to f bar of x plus p of x by 2 plus p of x prime by 2 truncated to L of x prime bits minus f bar of x, which is greater than or equal to f bar of x plus p of x by 2 plus p of x prime by 2 minus 1 by 2 to the L of x prime minus f bar of x. Now 1 over 2 to the L of x prime is less than or equal to p of x prime divided by 2. So this quantity is greater than or equal to f bar of x plus p of x by 2 plus p of x prime by 2 minus p of x prime by 2 minus f bar of x. In fact, this is a strictly greater than. So this quantity is greater than p of x by 2, which is 1 over 2 to the log 1 over p of x plus 1, which is greater than 1 over 2 to the ceil log 1 over p of x plus 1, which is simply 1 over 2 to the L of x. So what we've basically shown is that if we truncate f bar of x to L of x bits, then for any x not equal to x prime, we have f bar of x prime truncated to L of x prime bits minus f of x truncated to L of x bits being strictly greater than 1 over 2 to the L of x. Which means that the code word for x prime cannot be a prefix of the code word for x. Because if they had to be prefixes, if one has to be a prefix of the other, then the difference cannot be any more than 1 over 2 to the L of x. So what we end up with is a prefix-free code. Correct. If so this is true for not just for x prime equal to x plus 1, but in fact any x prime which is larger than x. The reason being, let's go back to the sequence of inequalities that we had. Suppose x prime is larger than x. All right, it could be x plus 1 or x plus 2 or so on. So f bar of x prime is definitely going to be greater than this particular quantity. If x prime is equal to x plus 1, then this is an equality. If it is, say, x plus 2, then you have a strict inequality over here. All right. So in any case, this quantity is greater than or equal to this. All right. Then everything else is the same. Nothing changes. Right. And for the lengths, when the lengths are equal to, when L of x is equal to 2 to the ceil log 1 over p of x plus 1. Sorry, L of x is, if L of x is ceil log 1 over p of x plus 1. The code is prefix-free. All right. So this code is called the Shannon-Fano-Elias code. All right. Okay, so far I have not done anything fancy, right? I came up with a code that is, okay, it's a different interpretation. It seems like a neat trick. It's a different way of constructing the code. Instead of constructing the code tree, I did this simply using numerical calculations. I took the probabilities, found the binary representation, truncated it, and got the code word. But in the end, I ended up with a code that had a larger expected length than the Huffman code. So why am I doing all of this? So firstly, so unlike the Huffman code, where if I wanted to get the code word for one particular symbol, I had to construct the entire code tree. In this case, if you think about it, if I want to find the code word for one symbol, I don't need to find the code words for any of the other symbols. Because the code word for a symbol x, this depends only on f bar of x and p of x. So if you give me f bar of x and p of x, then I can compute the code word. I don't need to find the code words for any of the other symbols. So if the alphabet size is large and I'm somehow able to compute f bar of x and p of x efficiently, then I'm done. I don't need to construct the rest of the code book. So that's an advantage. So encoding is in a sense more efficient. How do I decode this particular code? So what does the code word correspond to? The code word for a particular symbol x, I'll sort of interchangeably go between the binary string, which corresponds to the code word, and the number that corresponds to the binary representation of that particular code word. So this is effectively the same as f bar of x truncated to L of x bits. And if you think about it, I can decode this in the following way. So if I have the code word, then I can compute this particular quantity. All right. And here is a simple decoder. If the c of x is less than or equal to f bar of x, but greater than or equal to, and maybe strictly greater than, f bar of x minus 1. See, I have this binary string. Let me the decoding can be done as follows. So let's say that the code word is, say, C1, C2 up to CK. I first find summation I equal to 1 to k Ci 2 to the minus I. This is some real number between 0 and 1. If this quantity is less than or equal to f bar of x, but greater than or equal to f bar of x minus 1. So in other words, it lies in the interval f bar of x minus 1 up to f bar of x. Declare that the symbol is x.
Should it be open interval or can it close?
Which one?
F bar of x minus 1.
F bar of x minus 1. Okay, I think this should be open from the left and close to the right. So this is sort of an algebraic representation or interpretation of the Shannon-Fano-Elias code, but it's more helpful to think about the Shannon-Fano-Elias code in terms of in a more graphical manner. So let's draw the CDF corresponding to this particular distribution. What would the CDF look like? Let's say the first symbol, this is 0, 1, 2, 3. These are the symbols. And so on. So this is the CDF. Now for each x, the f bar of x is going to lie at the midpoint, right? So this particular height is p of x. This is p of 0. The height of this is equal to p of 1. The height of this is equal to p of 2, and so on. So f bar of x is essentially going to be the midpoint of these. So these will correspond to f bar of x. So this is f bar of 0. This is f bar of 1. This is f bar of 2, and so on. And all of these are numbers strictly between 0 and 1. All right? So if you take this f bar of, let's say, f bar of 2 to infinite precision, then the value would be exactly this particular quantity. When you truncate this, you get a number which is somewhere below f bar of 2. If you truncate too many bits, then potentially you could go lower and lower, right? The trick is you truncate just enough so that the corresponding code word is going to lie in this particular interval and not outside this interval, right? So if you allowed for more than a certain number of bits, then you're going to be closer to f bar of 2, right? So full precision would give you f bar of 2. You truncate a little bit, you get something a little lower. The more you truncate, the lower you'll go. So the trick is to truncate just enough so that you will always, so f bar, the truncation of f bar of 2 lies in this interval, the truncation of f bar of 1 lies in this interval, the truncation of f bar of 0 lies in this interval, and so on. All right. And you can also see that the room you have for truncation essentially depends on the length of this particular interval, which in a sense depends on the probability of x. Not just probability of x in this case, it depends on probability of x and also probability of x minus 1 in a sense. Right? But still we're giving enough room and making sure that this depends only on the probability of x. All right? So the basic idea behind the Shannon-Fano-Elias code is to take this is corresponding to each symbol, you associate an interval and give a representative point for each interval. Each of these intervals corresponds to the decoding regions of that corresponding symbol. So if the code word lies in this particular interval, then you're going to declare 2. If it lies in this interval here, you're going to declare 1. If it lies in this interval over here, you're going to declare 0, and so on. That's how decoding works. All right. So that's the Shannon-Fano-Elias code. All of this is nice interpretation and so on. And in a sense, we've got slightly better than Huffman codes because we can decode and encode efficiently. Decoding and encoding does not require you to produce the full code book. In Huffman codes, you had to construct the entire Huffman tree, even if you wanted to encode one particular symbol. But now I don't need to construct the rest of the code words. I can construct the code word for any individual symbol separately. Right? But as we'll see in the next class, you can go even one step further. If you want to encode a block of symbols, you can do that in a very efficient manner. And the main idea is just this, that to encode, all you need to know is f bar of x and p of x, nothing more. And there's a very efficient way, a very simple way of computing f bar of x and p of x with very low complexity. All right? Okay, so let's stop here.